All right. Okay. So if you caught last lecture we talked about, at the end of the last lecture, we talked about comparing these different methods, right? We talked detailed comparison of what finite difference versus spectral from basically 4 perspectives. Accuracy. The accuracy was clearly much better for spectral methods. You have infinite order accuracy compared to finite difference schemes, which gives you second order or fourth order. And for spectral methods have this spectral accuracy, which is supposed to be infinite order. So it's a win for spectral. Then we talked about implementation. The big deal with implementation with the FFT is really just have to remember if you're in the transform space or the real space, not a big deal. Finite difference, you have to build these matrices. Not that big a deal once you get them, right? But you still have to go through the work to get them. And you can recycle them now. Now that you have them, you have these matrices that take one x derivative and one y derivative and dx squared, dy squared. You can recycle them, but you always have to check to see if they're singular or something like that. So we did implementation. Then we also talked about, I can't remember exactly what the third thing was, but also spectral was better on that one too. And finally we talked about the last thing, which were boundary conditions. So out of the 4 things we talked about in terms of evaluating a scheme, spectral was clearly a winner on 3 of them. And then the last one, there was the boundary conditions. For boundary conditions, spectral is periodic, expanding of cosines and sines. This is a problem, right? Because in some sense, finite difference, you can do anything with them. Think about what we did for homework 1. You have those boundary conditions where it was decaying at the boundary. You could say, well, you just discretized the boundary condition. So finite difference has no problems with discretizing more complicated boundary conditions, but spectral does. That was the big win for finite difference. So, so getting back to the boundary condition issue, oh yeah, I remember what the one was. Computational speed. And n log n versus n squared. That was and clearly n log n is what you really want. So because you have all these advantages to using spectral methods, and almost across the board, if it weren't for the boundary conditions, there would be no contest between which method you would choose. It would just simply be spectral. But because of the boundary conditions, you have to think again about what that means, right? You have periodic, and that's what you have to work with. And a lot of problems you have solved don't have periodic boundary conditions. But given that, we're going to come back to this issue. Because Fourier transforms are so powerful, or spectral methods are so powerful, we're going to figure out, well, is there some way I can make it work? I'm going to really try because it's so powerful elsewise. Otherwise, I want to use boundary conditions, and in particular, revisit Chebyshev transforms. Because we knew that the Chebyshev transform was closely linked with the cosine transform. And that's an n log n operation, and it's spectral accuracy, so everything. So maybe we could somehow figure out how to do boundary conditions issues better with spectral methods. Okay, how to do periodic boundaries. Method 1. You could just say, you know what? I'm going to use the FFT anyway. I don't care that it's periodic, and I don't care that there's a function I'm trying to do that's not periodic. I'm going to use it anyway. What does that mean for you? What you do with this method is you can do a periodic extension of your domain. So what this does, it says, okay, suppose I have a function. And my function is, I don't know, yeah, let's go from -1 to 1, and my function is y equals x. Clearly not a periodic function. Okay. Fourier, in the early days of Fourier theory, said, okay, well, what do I do with functions like this? I mean, he made this very broad statement. He said, give me a function and I will write that function down in terms of cosines and sines. He never said anything about give me a periodic function, and I'll write them down as cosine and sine. No, he said, give me a function, any function. Okay? So the idea is to say, well, what he was saying is, okay, so this is a function on -1 to 1. And what Fourier theory says is, well, I can periodically extend this. So I have it on this interval. Well, why don't I just extend it periodically in these directions? So now my function is periodic. I mean, all I'm interested in is this range right here on this interval. But when I do expansion in terms of Fourier basis, really what I'm doing is something like this. Now, what's the problem with this? The problem with this is this jump. This discontinuity right there. Okay? So, what happens in this? Well, when you do this, you represent a function here. You can still do the expansion in terms of cosines and sines, or an FFT, which is basically that. And what ends up happening is, when you approximate this thing, you find what's called Gibbs Phenomenon. As you start increasing the number of Fourier modes, you get a really good approximation, but then the Gibbs phenomena is this wiggling at the edges where the jump occurs. In the limit, as you take an infinite number of Fourier modes, the solution that the Fourier mode series gives you is exactly on the line with, at the jump, it's the value in between the jump. And you're exactly on the line. But what we do know is from computations, you never do an infinite number of modes, right? You always say, I'm working with this number of modes, 2 to the n power, like 64, 128, 32. When you cut off, that means you're going to have some of this wiggle going on. So let me show you what it looks like. And we can probably zoom in here. Right here on the TV. Wow, yeah, that's kind of fancy. Okay, so here's my function, f of x. Here's its periodic extension. And then what I've done is I have gone ahead and plotted my periodic extension. And this is also in the notes. This is figure 29. With n equals 8 and n equals 16. So these are the number of Fourier modes. So n equals 8 is a dotted line you can see kind of underneath there. And n equals 16 is the dark line. You can see the wiggles. Hey, where are the wiggles? Anybody know the wiggles here? Do you guys know who the wiggles are? Kids show. Anyway, the kids show, there's 4 guys. They all wear different colored turtlenecks. And they say, hey, where are the wiggles? And they go, keep wiggling. My daughter loves it. They're from Australia. It would be an awesome life to be a wiggle. Yeah, you know, these guys dance around. They're not even that good at dancers. I mean, I could dance as good as them. And like, they're loaded, I think. I'm thinking, next life, I'm going to be a wiggle. Forget this math gig. So, anyway, there we are. We see the wiggles. And the Gibbs phenomena building up. So if you want to cut this down, you have to keep going up in Fourier modes. But the whole point, right, is when we do problems, is that we want to keep as few Fourier modes as possible, right? Because we want to run this thing quickly. So this is going to cost you. But this is one method for doing this. You say, okay, fine, my function isn't periodic. Fine. I'm still going to do an FFT anyway. This is the price you pay. Okay? Remember in the homework 2 that we're doing, when you put in the vorticity, you're putting in vorticity usually somewhere in the middle of your domain and watching what happens with it. And then you're watching it move or whatever. And it's periodic boundary conditions, so if it moves up through here, it comes back over here, no problem. But suppose you were to put in an initial condition into your code that wasn't periodic. In other words, suppose you put vorticity right there. In other words, it wasn't periodic and sitting over here too, just a big lump of vorticity there. Across this boundary, it would be discontinuous, and what you would see then, as you start to evolve it, you would get Gibbs phenomena on this edge. because that's not periodic. Okay, that's the consequence of that. That's the price you're paying. Okay, so this is one method that you can use. Method number 2. What is another method for representing these non-periodic functions? Well, another method for doing this is just polynomial approximation. In other words, you take a function and you say, all right, how about if I just oops, 0 to n, little n. Let's just expand it in terms of a bunch of a power series. Okay? This is fine. The nice thing about this is when you discretize a function, suppose I have a function. Suppose that's my function. And the idea is you discretize it, right? You cut up your domain, and what you say is, okay, I discretize this. How do I represent this function? Well, what I could do is say, hey, I can take a polynomial, and by picking my coefficients just right, I can make this function go through every single one of these points. I can pick A0, A1, A2. In fact, however number of points I have, right, if I have n plus 1 points, I have an nth degree polynomial that will guarantee to go through every single point. How I discretized it. The problem with that is this. Go back to that example. I have a line. And let's just suppose I cut it up into 10 intervals, so there's 11 points total. Something like that, okay? So just a bunch of points there. Now, if I had 11 points here, I'd have a 10th degree polynomial. I'd have something like A0 plus A1x plus A2x squared all the way to A10 x10. Now, what do you know about polynomials? What you know about polynomials is, for instance, x squared. X squared looks like this. X cubed, generically like this. X to the 4th, like this. And so forth, right? How many terms does it have in it? Think about it that way. So x squared has 1 term. X cubed, 2 minima and maxima. X to the 4th, 3 minima and maxima. So when you have x to the 10th, it has 9 minima and maxima. So when you try to say, let's put a polynomial through here, it's got to wiggle 9 times, right? This is a line. And you're putting this thing through here, so what ends up happening, you get actually a phenomena called polynomial wiggle. Okay? So even the wiggle thing is all over today's lecture. And also known as the rung phenomena. So same guy from Runge-Kutta, or polynomial wiggle. Because now you say, well, I have a 10th degree polynomial. Well, it has to turn 9 times. And what ends up happening is, when you actually do this, and in fact, it gets worse and worse, right? You keep adding number of points. Suppose I have 20 points in there. Then I have 20th degree polynomial. It's going to have 19 minima and maxima. And let me show you what happens. And here the function I'm looking at is the following. Take the following function, f of x equals 1 over 1 plus 16 x squared, which, by the way, just kind of looks like a bump, something like that. I say, okay, start approximating this thing with some number of you know, chop it up in a certain number of points and see what happens. Let me show you this here. You can't see what's below it right there. There we go. Perfect. Figure A and B. So figure A, what I've done is said, okay, 12 points. And look what happens. Along the peak of this pulse, or the peak of this function, it looks great. And what happens at the edges, though, is catastrophically bad. It has been all pent up trying to make this thing work here that it just goes nuts. You start seeing it wiggle, wiggle, huge, and then this thing just goes way down off the screen, way down south, and then it finally comes back. It goes through every point. So this drops very large negative and then comes back to this point. This is with n equals 12. It gets worse if you go to n equals 24. Again, it does a very nice job approximating the function, smoothing a very nice approximation through here in this region, but look what happens at the boundaries again. Look at these huge oscillations at the boundaries. Basically, then, if you use this kind of method, polynomial approximation, on this kind of evenly spaced grid, absolute trash. Especially if you want to start, you know, I mean, typically you want to cut this up to have nice resolution. It's only going to work nicely if you have really low resolution, right? I mean, if you have a line there, you want to put a line through it, not a huge polynomial. So this method is actually very bad because of the polynomial issue, polynomial wiggle issue. The third method, you say, okay, well, does that pretty much rule out polynomial fitting? Because, I mean, in some sense, polynomial fitting is a very nice thing, right? I mean, people know how to use it. It goes through all the points. There's no discontinuous jump, no periodic extension of the integral, nothing, or of the function. Which brings us to method 3. We're going to do polynomial fitting again. Let's try this again. Polynomial with clustered points. Now here's the idea behind this. Let's do the same thing we did before, okay? Which is expand, just like we did before in the previous case, some nth degree polynomial, which we know still has to have this property of wiggling. Peaks and so it's n minus 1 minimum and maxima. But now instead of, when we do this function, for instance, that we had over there, instead of evenly instead of having the points evenly spaced between negative and 1 and 1, let's say, I'm going to cluster them. I'm going to cluster them in a very specific way. I'm going to cluster them on the following points. My x points that I want them to be on are given by this. So what this does is you basically project down the placement of the points evenly spaced on the unit circle onto this negative 1 to 1 domain. And so what ends up happening is you get clustering of points at the boundaries, less in the middle, and then you're clustering of points at the other boundary. Okay? So this kind of idea, you say, well, what's the big win here? Is there a big win here? Well, we're going to see in a second that there is, in fact, a big win. And notice where I'm putting my points. You may not remember how many 2, 3, 4 lectures ago. 2, 3, I don't know. But those are the Chebyshev points. Okay? Remember when we used Chebyshev polynomials defined in terms of this transform between x of n and cosine? And this is what allowed us to use the fast Fourier transform, or the discrete cosine transform, because we could do this. And here's the other big win. And this is, again, why Chebyshev becomes powerful, is because I'm working on this clustered domain. So when I do this, can I approximate this function well or not? Remember, now I'm going to show all 4 pictures here. The top 2 is what I showed you previously with evenly spaced grid points. In particular, when I had n equals 12 and n equals 24, you can see it does a nice job, but then you get this huge amount of wiggle at the edges. So the polynomial wiggle basically makes this method up here completely useless. However, look what happens here. For this one here, what you see is the dark line here is okay, so the dots are the unequally spaced domain for n equals 12 and 24, and the dark line is the actual function now, the polynomial fit to it. It doesn't go nuts at the boundaries. You can see it sort of wiggling right there around. And in fact, what's interesting is before, as we increased the resolution, what happened? Bigger and bigger and tighter wiggles. Here, as I increase the resolution, it smooths it completely out. So I get more and more accurate, which is exactly what you want. You want to be able to increase the number of points you have representing your function and increase accuracy in turn. The last thing you want to do is, hey, I want to get more accurate because the rest of your code, the accuracy is going to depend upon the number of points. So you want to increase your points, and you'd hate to have one piece of the code saying, by the way, if you keep increasing, I'm going to get worse and worse because everybody else is getting better and better. Okay? So this is really nice. It does a really good job of approximating the function. Okay? So this method is not bad. So in some sense, we have 2 methods that we might think about using. Method 1, which is just a periodic extension. Use your FFT anyway. Say, I don't care. I know I don't satisfy the boundary. Do it anyway. But this method here is nice because, in fact, just by putting on an unevenly spaced domain, basically you get incredible accuracy. You don't have any of the Gibbs phenomena. So this is really quite a nice method. And you can see, it brings us back to the Chebyshev points, which is this natural connection between Chebyshev points back to the discrete cosine transform. So it already tells us that, hey, if I do this, I already get this accuracy, plus I can use n log n operations in doing it. Okay? All right. So let's pursue this method. Race everybody else here. Okay. Clustered points. And now we're going to talk about also Chebyshev differentiation. All right? So how do we go about constructing the ideas for using Chebyshev? So let's come back over to here. The idea here is that if you use on this domain, you now have your function given by here. F of x equals a of n, x of n. Okay? So all you really got to do is figure out what the coefficients a of n are, which aren't that hard to do. But here's the beauty of this. How hard is that to differentiate? That's really easy. Right? Because it's just your power rule. It's the first thing you learn in calculus, I think. That's the first thing you learn how to differentiate, right? Is like the first general rule is x to the n is n x to the n minus 1, right? Okay. So, in some sense, once we get this representation down, all we have to do is think about, well, how do I take the derivative of this? It's pretty easy. So what we want to think about doing is, how do I then make a function to represent it, and then differentiate that function? So here's the 2-step procedure. First, let P be a unique polynomial. So P is our polynomial of degree less than or equal to n, let's say, with P of xn so every point of this polynomial goes through a point of what the function is, okay, where v of x is the function we're approximating. Okay, so we're trying to approximate this function v of x, and we put a polynomial through it. It goes through a bunch of the points with some degree. Okay? Then, remember, why am I concentrating on derivatives? Because the whole idea is to solve these PDEs, ODEs, using the Chebyshev transform. And so what you really need to know is, how does the function relate to its derivatives? That's the biggest thing in Fourier transforms. Once you know that, if you take the derivative of the Fourier transform, all you get is take the Fourier transform of the derivative, all you get out is an IK popping out. Once you know that, then you can just apply it to all these problems. That's the fundamental thing you need to know. Same thing here. Okay? Once you get this, then you say, okay, to take the derivative, differentiate. So then you get just the derivative of the polynomial for each point. Right? So you have to evaluate this polynomial at each of the data points. That gives you the derivative at each of the data points. So essentially, this turns out to be a just like everything else, matrix multiplication. Okay? And all we have to do is figure out what the matrix D of n is. I'm going to give you the matrix D of n. And in fact, on Monday's lecture, we're going to do a little classroom example using the Chebyshev polynomial stuff. And not only will I give you the D of n, we'll play with it in class and show that in fact it does take the derivatives the way we want it to. And so it's going to be just a function call for you to actually access this matrix D of n. Now notice the thing is, you give me the number, you give me the degree of polynomial you want to work with. In other words, the spatial discretization, you can construct this D of n. So what you need is an algorithm saying, I want 50 points. That's my D of n. Okay? That's what I'm going to give you on Monday. What does D of n look like, by the way? Here are the components. This is the key to the whole thing, so this is where it kind of gets a little boring, but you kind of got to see it. All right. So D of n is n plus 1 by n plus 1 matrix. Remember, that's the degree of the polynomial, but there's the a0 plus a1x, so there's actually n plus 1 terms in it. Okay? And here's what the components are. The 0th component is that. The last that's the first diagonal. The last diagonal is minus that. Here is those are all the diagonal elements. And here are the off-diagonal elements. So you have to just load up the matrix with these terms. So what in the end, what it kind of looks like is the following. D of n has the following structure. Up here you have 2n squared plus 1 over 6. And then along this top row, you get 2 minus 1 to the j over 1 minus xj. This term over here is minus 1 n over 2. And then this first column, you have minus 1 to the I, 2, 1 minus xi. You know, it might be actually helpful just to use this again here. We'll zoom in right there. There's what the matrix looks like. So you see that you have here's your first diagonal, last diagonal as advertised. Your opposite of the diagonals are fairly simple. Your diagonal elements, your off-diagonal elements, and the first and last row, first, second column, all have a kind of a more simplistic structure than you would get in sort of in the interior of this thing. Okay? So this is just a big matrix, and it's just a bunch of algebra to get it. And so really what you want to do with something like this is just simply automate it. And that's what we're going to do. We're going to a little routine that just does this. And all this matrix does is this operation right here. You fit the thing, you want to differentiate it, there you are. Multiply it by matrix. Couple things that we got to note about this first. This matrix here is full. All the components are full. Compare that to what we did with finite difference. Finite difference, we had this sparse structure. We had only a few diagonals that mattered. When we did 2 derivatives in x, 2 derivatives in y, all that mattered was 9 diagonals total. Okay? And then when we did 1 derivative in x, 4 diagonals mattered. 1 derivative in y, 4 diagonals mattered. This is full. This thing is just loaded up everywhere. Now, the one consequence of this is that your operation counts can be a little higher, right? Because when we had a sparse matrix, there's a bunch of zeros there. And in fact, we put it with SP diag, so all it saved was the sparse structure. So when you took a vector and multiplied it by it, it'd say, hey, that's almost all 0, so I'm only going to do operations on the things that matter. Here, I've got to do the full set of operations. Multiply every component, add it, so forth. So the hope is that this is a lot more accurate. They can take a lot fewer modes. Because in other words, if you take the same size matrix here as you do with your finite difference is going to be a lot faster. This has spectral accuracy. So the idea is you say for the same accuracy, I could take a lot smaller matrix. Okay? That should be, you should understand that. That's your trade-off. Otherwise, you don't want to go this route. Okay? All right. And once you build this matrix, then you can easily say, okay, I got my D matrix. Then, even something like this, if I take a differential equation, if I wanted to solve this, notice what you do with this thing. If you want to use this representation, what you do is basically you can, how do I take 2 derivatives here? First, you can represent the solution as a vector. And you say, oh, well, 2 derivatives, all I have to do is dn squared. There's 2 derivatives. Right? You want an nth derivative? Raise it to the nth power. So this matrix, once you have 1 derivative, you can get all of them very easily. Okay? Then you could do that, and then plus alpha dn times u. What is that? Equals f of x. Okay? And if you did something like this, what you'd end up with is a big system of equations you can just then do a backslash on, you're done. That's like a boundary value problem. What we're going to mostly be doing is ut plus this, is equal, or put that over there like that, right? The idea of what we want to do, how we want to use it, is more in this configuration here, which is to say, when I have a partial differential equation, my whole aim is to turn it into a set of differential equations. And so you'd get, this derivative matrix basically discretizes this derivative, discretizes that derivative. And now you have this huge set of first order ODEs. You throw it into ODE4-5. You let it run. You get your answer back out. Okay? All right. Now, thus far, we haven't even talked about boundary conditions. So we need to add that as the next step to this thing here, which is, how did we determine boundary conditions before? We determined, typically we're applying boundary conditions to the first and last point, right? So, it's this. Boundaries. So, for instance, we might have the boundary conditions that are the following. How about v at -1 is equal to v of 1 is equal to 0? Okay? Notice that these aren't periodic boundary conditions, right? I mean, you're clamping the solution. The solution could look periodic still with these boundary conditions, but not necessarily. For instance, you could have a solution that does something like this. That's not periodic. Because periodic, it has to look more like something like this. So in other words, when it continues up, there's no kinks. Okay? Now, our solution, or the idea behind it, let's come back to this idea here. I want to take the derivative of the function and know how to take the derivative, but I want to preserve the boundary conditions. So V is a collection of points. So let's write this down. We have this. So I have this big matrix D, V, which is V0, V1, Vn minus 1, Vn. So if I take this matrix V, multiply by this matrix, I get back out my matrix W, which is the derivative. And then I have this top row here. I'm going to say, okay. And notice, the one thing I know is V0 and V of n. Those are my boundaries, right? When I multiply this out, V0 and V of n only affect this first column and the last column. When I multiply that out, V0 multiplies these guys in the first column, Vn in the last one. Not only that, my derivative, for instance, may have a boundary condition associated with that. Well, that's W0 and W of n, which are corresponding to the top row and the bottom row. So the only things you need to worry about in setting up your code and the kind of modifications you're going to make is that basically the only thing that needs to be affected are these edge rows. Top and bottom row, first and last column. The interior of the matrix doesn't matter. It's not affected by the boundary conditions. Not directly. Indirectly it is. Okay? So in the end, really, for instance, for these simplified boundary conditions, all I'm saying is that's 0 and that's 0. I already know them. I don't need to solve for them. All I need to solve for is the middle points. So really, I want to solve for some v tilde, which is v1 to vn minus 1. The interior points. Okay? This is a lot like what we did with the direct solve method for homework 1. You pull out the interior points, and what you want to do then is say, okay, how do the interior points get differentiated? Well, then there's some vector w tilde is d tilde times v tilde. Okay? Where this d tilde just is simply this middle box of this matrix. How do you get that middle box out? Pretty easily, actually. Tilde d is equal to, you take the D matrix, goes from 2 to the nth row to the nth column. And that will grab out the interior, because there's 1 to n plus 1 rows, 1 to n plus 1 columns. This just thing basically grabs the middle. And then you can apply this, and that differentiates every one of the interior components. Okay? All right. Last thing. Well, maybe I'll just kind of wrap up here. So I've just briefly discussed this and touched on this. So what we really need to do is we need to get a little bit more explicit about how to do this. Okay? So what we're going to do in class on Monday, I'll bring the computer in. What we're going to do is, first of all, I'm going to give you this D matrix, which is full. We'll see what it looks like. We'll start differentiating things. Start doing stuff basically on this grid that is non-uniformly spaced. So there's actually a couple things that need to happen here. One is you first need to find your, so when we go back again to this here, not only do we need to find the function, we need to find the points I'm actually differentiating on. So I need to define my clustered domain. Remember, when we do a lot of our problems so far, we've always just said, okay, let's take L to be 20, and x2 is a linear space between negative L over 2 to L over 2 and this many points. And it does it equally spaced points. We can't do that anymore. Right, we've got to say, okay, it's more complicated. Now I've got to put my domain on cosines. Okay? So you need two parts to do. First, you need to put your domain on this clustered grid. Then you need to define this D matrix. Once you have those two, you have the two fundamental building blocks for doing any of the partial differential equations at that point. And the third thing you need to do, the third thing you need to do, okay, is how do you practically implement boundary conditions? And there's some really easy boundary conditions to implement, especially with Chebyshev, which are 0, pinning the boundaries, or taking the first derivative be 0. Okay? And so we'll talk about how you do those, because I think in the last homework we will be doing that. And then the final comment. Although there is this connection between Chebyshev and FFTs, the discrete cosine transform has actually, I made this said this in class previously, the discrete cosine transform is now shipped to the signal processing toolbox. So you have to pay extra to get that. So that's a problem, right? Because this is what you should be using to make it fast. So we're not going to make it fast. We're just going to use this full matrix, which will be slow. That's okay. The idea is there. It's still spectrally accurate. You're using a different basis, but the connection now is, we're not going to actually then do the one step further, which is now let's tie in the discrete cosine transform to make it n log n. Okay. Have a great weekend. Office hours today, same, 2 to 3:30, if you guys have any questions.